This short video is created to add some additional information, provide a little bit more information and clarity on a few things that had some errors, especially in the truth tables of some of the logicals of the equivalency laws, and then finalize the topics of section 1.3, reminding everyone that the quiz will include all notes of sections 1.2, 1.1, 1.1, and 1.3. So let me go over by starting once again with the logic laws. So summary of the logic laws of the equivalence. These additional notes, by the way, are posted in the lecture notes module in the Brightspace. Two compound propositions are equivalent if they both have the same truth values. So we say, let's keep it like simple propositions P and Q. They're equivalent if they both share the same truth values. If P and Q are two simple propositions, we say P is equivalent to Q if the two statements share the same truth values. So if that is the case, now it is important to say that the notation is equivalent to, it's not the same as the notation equal to. In the list of logic laws, we mentioned today the De Morgan's law, the negation of P or Q, and the negation of P and Q. When you negate P or Q, this is equivalent to negating P and negating Q. When you negate P and Q, this is equivalent to negating P or negating Q. We mentioned the identity laws for the De Morgan's law and the identities law. We use the truth value tables, and then we prove that these are both sides are equivalent to one another. P or F is equivalent to P, and P and T is equivalent to P. Domination's law, P or T is equivalent to T, and P and F is equivalent to F. We mentioned the commutative laws, very similar, and the associative, very similar to same laws that are used for the two important operators, multiplication and division, when it comes to regular numbers. So the commutative laws for the disjunction and conjunction, P or Q is equivalent to Q or P, and P and Q is equivalent to Q and P. And the associative law allow you to group propositions together. So if we have P or the quantity Q or R, then this is equivalent to grouping P or Q together or R. And this is true for the conjunction and P and the quantity Q and R is equivalent to the quantity P and Q and R. The same as the distributive property per multiplication over addition, we have the distributive laws for and or. So P or Q and R can be distributed into P or Q and P or R. And P and Q or R can be distributed into P and Q or P and R. Now please pay attention to the corrected form of the negation law. So this has to be correctly P disjuncted with not P. So P or not P is equivalent to the proposition true, and P and not P is equivalent to proposition F. We do have a double negation law for any single proposition. If you double negate P, this is equivalent to P. And now let's see if we can use some of these logical equivalences to show that the logical laws are making statements equivalent to one another. So let's prove that negating Q and not P is equivalent to P or negating Q. So let's, without using the truth table, I'm going to stick with the laws of the equivalency. And then the laws of the equivalency will allow us step by step to show that these two sides are equivalent to each other. So let's start off with the left-hand side. Not the quantity Q and not P. So I'm going to negate both statements inside parentheses. So this is equivalent to negating Q. The N becomes an OR, and negating not P. This comes directly from the De Morgan's law. I'm going to keep not Q as it is. I'm going to keep the notation of the disjunction OR as it is. And then pay attention to another law, which is the double negation law. And not negating not P becomes a P. So now we have not Q or P is equivalent to, and then if I use the commutative law for the disjunction, we can write this as P or not Q, making the two statements the same. Also, we had a question for the negation. We had a question for the connection of or the laws of the implications. So the equivalency laws do include a law for implications. The law allows us to substitute the implication of P to Q, so P implying Q, to the following statement. P implies Q is equivalent to not P or Q. So with that in mind, this is the last law. Let's go ahead and then try to work with some statements, trying to find a form that is going to be equivalent to the given one. So the given one is not Q implies not P. So this is a typical question one of you asked today in class. The implication with the negations of the two symbol statements or prepositions Q and P. So Q not Q implies not P is, according to the implication law, is equal to negating the first one, so negating not Q, changing the implication notation into an OR, and then keeping the second one as it is. So this becomes now a double negation of Q or not P. But according to the double negation law, negating not Q becomes a Q, or stays the same, not P. So the statement not Q implies not P is the same as Q or not P. Find the equivalent form of not R and P implies Q. So what is, according to the implication law for the equivalency, not R and P implying Q is equivalent to negating the first one, so we negate the quantity inside parentheses, change the implication into a disjunction or, and keeping the second statement as it is. So this is based on the implication equivalency law. So you keep in the second as it is, the implies becomes an or, and then you negate in the first statement. So we negated the quantity inside parentheses, implies becomes an or, Q stays as it is. Now we'll continue to operate with this. If you, according to De Morgan law, if you negate a statement such as this one, which is a conjunction statement, that means you're going to negate the first one, so you get a double negation of R. You're going to change and into an OR, and you're going to keep P as it is. And then, of course, the last part of it, or Q, stays the same. The double equivalency law of negation generates an R. Then we have or not P or Q. Then you can associate R or not P together, and then or Q, keep it as it is at the end, which is pretty much the final step of these additional notes for a couple of things that generated some errors. Now, the other thing I'm going to mention, I'm going to exit out this video go back to the lecture notes, and then I'll focus on something different. Focusing on two spatial prepositions, complex prepositions. One of them is a preposition that is always true, and that is called a tautology. And then the other one is a group of prepositions that are always false, known as contradiction. As a matter of fact, I added at the very top of my notes a simple example of a contradiction. Without using the truth values tables, now we can use the laws of equivalency to go step by step and show that this is indeed a contradiction, which means it's always false. So let's show that negation of Q imply P or P is indeed a contradiction. So to prove that this is indeed a contradiction, that means this is equivalent to F. So let's get started. So I'm going to start off with the left-hand side, which is negating the expression Q implies P. So that's the quantity inside parentheses, or P, making this equivalent to F. Now, I would say in this particular case, the example that is directly in the lecture notes, and then I copied this example directly from the lecture notes, and then I updated the lecture notes, the ones that are typed in, has an error um, between the quantity that is inside parentheses and the P. It's supposed to be an and, not an or. And then, as a matter of fact, when I went through the proof, in order for this to be in contradiction, this has to be an and, not an or. If you use an or, this is indeed a tautology, it's not a contradiction. But let's stick with an and. So this particular operator must be an and, not an or. So we start off with what is given, and then correctly what is given is negating Q implies P, and P is equivalent to false. So since I have an implication inside parentheses, I'm going to turn this implication using the implication equivalency law. So Q implies P is the same as negating Q or P, and keep everything else as it is. So the negation sign outside parentheses is the same. This is the operator and. Remember, the original example was given with the type or. So now I correct it as part of looking at some errors and generating the correct solutions. So the correct operator must be an and you see now it is corrected into an and. So the expression, once again, that we are proving that is a contradiction, the correct expression must be negate the implication Q to P, or Q implies P, and P. So it should be an operator and between parentheses and P. And then in my first step, I'm trying to show it's a contradiction. I'm trying to show that this is equals to F. I started off by changing the implication, Q implies P, using the implication equivalency law. The law is saying negate the first statement, so I'm negating Q, change the implication operator into an OR, and keep P as it is. And that's what I did right there. And everything else stays the same. The negation sign outside is the same, and then this correct form of operator and is the same. So now let's continue. I'm going to use the De Morgan law and then apply this negation sign outside parentheses. So when I negate the expression inside, that is going to be negating not Q, negating not Q. The or inside parentheses becomes an and then negating P, and then negating P. Everything else and P stays the same. According to the double equivalency law, this double negation of Q becomes a Q and stays the same. And then we have negate P and negate P and P. And then I'm going to use the associative law. So pretty much associating not P and P together and keeping Q outside. So Q and not P and P. Not P and P is indeed one of the laws that we used in the previous statement. This is the negation law that, again, I had to make corrections. It was originally not Q and P. Now, correctly must be not P and P. Not P and P, according to the negation law, is an F, and then Q and F is indeed an F.